Now, every object file that is output by the compiler will have a relocation section. Now, this relocation section tells the linker which are the symbols that are not resolved. For example, we saw in the function call previously that it does a branch to 0. So the compiler does not know where that function resides. So whatever the compiler does not know, it lists in the relocation section. So when the linker sees this particular object file, say for main, it knows which are the symbols it has to fix. So it looks for those symbols in the other files and fixes it in this particular file. Rather, it fixes it in the output object file, that is the integrated object file that is a combination of these 3 input files. So the linker has to know about the list of symbols in the current file that needs fix up. In other words, absolute or relative addresses of the symbols are unknown currently. So we do not know where they are and what their addresses are going to be. We just know, probably we know the value of the symbols. These are all calls. Calls means these are all functions and these are some variable values. Okay. So like we have done so far, let us go into the terminal and try to view the relocation section for the input files. So to view the relocation section, we will use the read elf command. So we do a read elf and then all, and then we do build example main.o. Okay, and we hope to see the section which has the relocation. So can you see this section? This section has the relocation information for this particular file. So we have PLL init 84 megahertz call, which we do not have any information about. Enable LEDs, we do not know. Enable sysdig, we do not know. Test3, test5, we do not know. Okay, so these are the symbols that needs fix up, right? Similarly, so linker, when it sees this file, it makes a note of all this, saying that these are the symbols that it needs to fix up, and this information has been passed to the linker by the compiler. So the compiler has created this table. Similarly, if we want to see the relocation information for, say, the configuration file, just a moment. So say, hang on. So say it's core initialization file. So let's say that we do want to check the core initialization file .o. So here let's look at the relocation section. So here we see that there is the relocation section that we are interested with is this. So it does not know the toggle LED information, EP0 state machine and EP2 state machine information. So this is the information that it is looking for. Okay, so this is an ARM thumb call. Though the toggle LED is still in that file, still it has put in a relocation information for this particular value. So let us do one thing. Let us go into that particular object file for core initialization and see what has been put in the toggle LED section. Okay, toggle LED call. So we'll know better why the toggle LED has not been has been put into the relocation section. So let's do that. So we do obj dump, and this time we are going to do for core initialization.o. So this will give us the and we'll have to look into the text section of the particular file. So let us see. So the call for toggle LED has been made here. So BL, it's BL. There is a value that it says it is calling, but still. So you see BL1FC here. It is calling the value from here, but still it is not fully resolved. Check this out. So it still needs some more information about this particular function. So that is the reason we can see that in the relocation information. And when we finally link all these files, we will see what value it has assigned to this. Then we will know what was missing and why this was put into the relocation section. So that is the information about the relocation section, so the compiler informing the linker about the symbols that need fix up. This is a very simplistic depiction of how the linker works. The actual operation is much more complicated, but then just to give you a basic idea of what happens initially, we will anyway go through this diagram. So as you know, these files, the input files, are compiled and object files are created by the compiler, and all of the files, because the compiler does not know about the existence of the other files, it guesses about the existence of the other files. It knows that other files can exist, and that is why it creates the object file with all that information for the linker, but it specifically does not know what other files exist in the pipeline to be compiled. Okay? Rather, it does not know what symbols, it does not have any detail about this, about where those symbols exist. That is not the job of the compiler. Anyway, so now suppose the module 1 is compiled with between addresses 0 to 399. Module 2 is compiled again between 0 to 599. So this is 400, say 400 bytes. This is 600 bytes, counting 0 in, and this is 500 bytes. Okay. Now all the addresses start from 0. So we have seen that also when we checked our .text section. Every .text section that we checked, all start from 0, 0, 0. Okay. So at this point, these three files are almost independent. When it is fed into the linker, it takes the order of input files that are fed into the linker. Okay. And if there are no specific instructions to have any section of the files to be placed first, which we have to do, it simply adds these. So the output file is going to be these three files combined together. So naturally, it will leave the first input file's address from 0 to 399, and it will start adjusting the address of the memory locations for the second file and third file respectively. So for example, 0 to 599 becomes 400 to 999, 0 to 499 becomes 1000 to 1499. So what is happening here? The address locations of the instructions are changing. Now, so if the address locations of the instructions change, naturally, we will have to change a lot of other things also, because say if there was a function call here, which was, say that function call was made within this file at some address location, say 400. Okay, so but when it comes here, the address location is no more 400. It is 399 plus 400, right? Because say this is just, conceptually speaking. So say there was a function call which was made at say BL. It was like 400 within this. Now, when all these files are brought together, this address is no more 400, right? Because this is actually starting from 400. So what needs to be done is we have to add 400 to the offset here. So it becomes BL 800. That is, this is where the new function call address is going to be. And that is the job of the linker, to fix up all the address. Not only, so one job of the linker is of course to find out so there is a function call made where the compiler doesn't even know where that function is. So that is one job the linker has. Another job the linker has is if it has to offset all the calls, everything by the number of bytes. This is going to be pushed down below the first module, right? So that is how the linker actually adjusts your addresses, calling addresses, and so on and so forth. So we'll see that in detail later. This is roughly what the job of the linker is. Now this is something that we had seen previously. That is the segment types. So this is mentioned here because there's a little more detailed diagram coming up. So we saw that in the compiler splits all the sections up into text and relocation, data, BSS, RO data, so on and so forth. So we saw that for the 3 files, these are the 3 different section headers. One thing you need to be aware of is here a section is created which is called ISR vector, and that section is not there in the other two headers. Okay. Now this is something that has been created by the user, that has been created by you. That is the ISR vector. Okay, and the ISR vector is going to have some a very important section actually, and you can see that the size of the section is 218 hex. Okay, and offset is AA4 in this particular file, and it is information. Okay, it is a data basically, but this is created by you. That is created by the user. Okay, and that is the reason why this is showing. So you can create your own sections if you wish for some. And what we are going to do when we see the linker script is we are going to place this section at the top, because this has to be the first section, because this is going to have the exception vector table. So we'll see that. Now this is again a normal, we have not created any new section here. So this is just as is what the compiler has output. Now this is a slightly more complex diagram from whatever we saw. Now here previously we assumed that it's just a flat file with code, and we integrated all the 3 files into one, and we talked about the address and how the addresses are moved around. But in this case, of course, what we saw previously, every file has a text section, data section, and a BSS section. And the BSS section is dotted because though this section exists but logically, but there is no storage actual storage that is allocated in the flash for 0 initialized data. What the information that we only extract is the size of the BSS section. That's all. So if we get the size of the BSS section, we will have to manually fill up that particular area of RAM with 0 initialized values for BSS. That is what we need to do. So that is the reason this is in dotted. So now we are seeing this is slightly more complicated depiction of the linker, where what happens is you have all these 3 files. Say there are 3 files which we are working with. Now the text section of all these 3 files are actually merged into one part of the output file. So the text section is merged into one. Then you have the data section, which is merged into the second part. So the data section goes like this, here, 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 and then the BSS section, nothing comes here, but logically, virtually, this is what is supposed to happen. Okay, and of course each section is combined after word alignment. So there is an alignment going on here, which is done automatically by the linker, and the word alignment is happening. So whatever we talked about, that is adjusting the addresses, and then for the function, if there is a function call which you need to move the address of the particular function call to some other address because it has been pushed down in this region, all of that is done by the linker here. So as you can see, text databases, all of the text gets combined here, data gets combined here, and BSS gets combined here, but virtually. It does not actually occupy any space in the flush. Now let's run the linker now on the 3 object files, and let's check the output. We'll check the text section and we'll check the section headers and so on. This is just to show you what the linker does. And after this, we will, of course, go through symbol tables and a lot of other topics. But for now, let us just have a look at how the output object file looks like after the linker runs on the 3 input object files. Okay, so let's do that. We already have this. So let's clear the display and let us do the link. So this is the linker command that we are going to run. So we'll just show you the command. So this is, so it's linker. For linker it is arm none EAVI LD, and then -t is the command for adding an external linker file, which is build_example.ld in our case. .map actually is asking the linker file to create a build_example.map file. That is, we will see the map file also. This will give us an entire map of where the linker has placed the different sections. Okay, and then we do a build_example.out and these are the files, and build_example.out is the file that we desire to have. That is output of the linker. That's a combination of all these 3 files, and these are the input files. Now, if you remember, we had tried out, as a side note, we saw what happens if we drop the -g information for in one of the input files, right? So let us bring back the -g option in that particular compile command, because since we want to see the output now, we don't want it to be missing information, because so we are actually bringing back the debug information for this particular file. Now let us do the link again, and this is the output file. So what we have got is the build_example.out, and we have got another file called the map, that is a build_example.map. So we are going to have a look at both the files. Let us have a look at the build_example.out file, and there were some missing symbols that we saw that was not resolved. So we'll have a look at that as well. So let's do this. So we'll have to run an obj dump command, but this time we'll have to do it on the build_example.out. So let us do, so we have the obj dump, and in this case it is going to be build_example.out. Don't put, so if you want to keep it absolutely distinct, then better name it something else here. I have just made it as build_example.out. You can just name it as something else so that you don't mix up, because there is already another file called build_example.main, build_example.main.o. So you might get confused here. So let's see what the output is. Now this is going to be a long file because we have the combined code of all the 3 input object files. So this is a disassembly of section.txt, and we have and that again, the text section, as you can see, is going to have a lot more information, and the sizes and everything are going to be bigger than so this size is 54C, and that is a combination of the size of the text section of all the 3 object files. So we'll see that later also. The data is going to be 5 because the .bss section is also going to be, also going to be higher, and so on and so forth. So this is because, and one thing that you need to see is and we'll talk about VMA and LMA. The starting address was 0 all through, if you remember. Now the starting address starts from this here, 8 with 6 zeros, 8000000. That is done by the linker. So when we see the linker script, we'll know that how this information is being put in here. So the complete, all the code, whatever text section that you will see here, is going to be starting from this value now. So there is virtual memory address is this and the LMA is also this. But when we come to the data section, you'll see that the VMA and the LMA changes. Now we'll talk about why the VMA and LMA has changed. So even for the BSS section, again, we see that the VMA and LMA are different. So we'll talk about that in detail, but let's see what it has made of the, we are not even looking at the symbol table now. We'll look at the symbol table later. We'll come back to this. So it has resolved all the symbols actually now, because it is the final output. This is a vector table, but let's have a look at the code. So the first thing that strikes us is it has adjusted the starting address of the main. So can you see it has changed the address to now 8000194. Previously it all started from 0. So all 3 files, everything started from address 0. So all the 3 different components all started from 0. But now we'll see that the start address is this, and the data that you see that comes along after this all have increasing address from this. So there's no repeat, there's no going back to address 0 and all that stuff. So it's a linear address space that the linker has created. Let's see the function call. We saw that there was a BL0 here, but now it has resolved that, and we can see that this is now BL 80001F0. See this. Then there's enable sysdig. So enable sysdig, again, it has got a proper address to this. It was 0 previously, and not only was it 0, it had some, this started from memory location 0 previously. So now since it's starting from this, it is also adding the offset of a higher address value. So 8001F0. Okay, 0001F0. Then similarly this one, demo relocatable. And demo relocatable is again, these two are in the same, it was in the same file, right? So the demo relocatable, just a moment, let's see the call here. Yeah, here. So we have made a call 8001DC. So if you see previously, demo relocatable would have been in 1DC, which is now adjusted to 8001DC because it is moved to 80000000. Okay, and demo relocatable was in the same file. Now let's look at one more issue we saw where there's a call for toggle LED. So there was a toggle LED call. So this is the toggle LED function, and now the function address has come to this 80003EC. And we saw that there was an issue with, not an issue, but it was kept in the sysdig handler. So now you can see that it has resolved it to 8003EC and there is no problems. Previously, even though it had called that function from here, still it needed some fixing up, which it has done now. So it is now 8003EC, which is a fix up that has been made. So I hope you get a rough idea about what has gotten fixed up. Okay, that is, the initial addresses have gotten fixed up. And one more thing is, for example, if you are seeing this part, since all offsets have gotten fixed up, even we saw the RCC, we saw the RCC getting adjusted, PLL CFGR. So suppose let's have a look at this. So RCC PLL, this part. So we saw this before, and we had talked about the offset being added to this particular function, remember? So the offset that we saw, 152 and 148, are the same because it is an offset to the PC. So this has not changed. Okay, so this is something interesting. This offset has not changed, but the entire address has changed. So this particular line has moved to a different memory location here. Similarly, this line has moved to though the offset has remained the same, because say this was it was 200 and this was 230. So the offset was 30 between these two addresses. Now if you do 8000, okay, 200 and 8000230, still the offset is 30. Okay, offset is still 30, but the address has just been moved. So that is one advantage of having a PC relative addressing. So here the linker has to work a little less. It does not have to change everything here, but it has just changed the absolute address here, and this has gotten addressed anyway. Okay, so this is how the linker has fixed up the output file for symbols that it could not address, and now the output file that you see has completely got all the addresses resolved, all the function calls resolved, all the variables resolved. Everything is as it should be. Now let us see the test 6 and test 4 and test 5 values that we had a doubt about. So I think test 5 and test 3, and as you can see, they have been put into the BSS section, and they are like 4 bytes. Previously this was not resolved. So all of this has been done. So again, going forward, now we are going to see from the next few slides, we are going to see how this happens. In the sense, we'll talk about the symbol table, and we'll go into some more detail. We'll see the linker script and how to write a linker script, and so on and so forth. And what is virtual memory address, what is logical memory address. So I hope that you understand what the linker is doing now, roughly. Okay, fixing up the addresses, and we'll have some more slides coming up which will again re-emphasize on what we saw right now. And hopefully by the end of this section, you will not be having any doubts about how linkers work.